Hello class. Today we're going to be talking about decoders. And the nice thing about doing the videos like this is each one will be self-contained. So we're only going to talk about decoders today, and then future videos will have specific topics pertaining to those. These are definitely in your homework. The next lab, Lab 5.3, deals with it. So these are on homework. Lab 5.3. They're on the quiz. They're on tests. What is a decoder? It's a device that selects one of multiple output lines based on an input value. So let's kind of look at one and describe it and give its truth table. So here's our input lines. 2 bits means we have 4 possible output values. We have 4 values, 0, 0, 0, 1, 1, 0, 1, 1. So this is known as a 2 to 4 decoder. You could also put a min term with each one of these. You can think of this as being A naught, B naught, 0, 0. A naught, B, A, B naught, A, B. We also oftentimes label these outputs D0, D1, D2, D3. So here's our truth table. If the input is 0, 0, then D0 is a 1, everything else is a 0. I should point out this is an active high decoder. Let me pause for just a moment. I should have said this at the beginning of the video. I've also attached several 2 to 4 decoders, 6 of them. Really, everything listed here except what I have highlighted is what you want to get. So let me highlight everything that you should be getting and have ready to go. We'll be looking at all of these today. And of special importance, the 74138 decoder is the one you'll use for lab. If we were actually going to be in the lab, we actually have that chip. We're not going to be in the lab, so you'll use the simulated version of that chip that I've created for you. All right, back to paper. Decoder here. If 0, 1 is the input, then input 1 is active. Everything else is inactive. And just follow the pattern along. So notice here with this decoder, one of these outputs is on at all times. We can also add an enable line, which allows us to turn the whole thing off. And so that would look like this. Label this as enable. So this is now an active high decoder with active high enable. I'm flipping my book to make sure I get things correct. So normally with 3 inputs, we'd have 8 rows in the truth table. But because the enable line turns everything off, we can actually reduce it. Make it a little bit easier. If enable is 0, we don't care what A and B are. everything is off. So that's how we turn the whole thing off. Then enable would be 1 for the next 4 rows. And that's what we have. And output 3 on the last row. So let's go ahead and take a look at these in Logisim. But before I do that, like I said, you've got these circuits online. You can pull them up and follow along. I encourage you to do that. Pause the video at any point. Play around with the circuit. Come up with questions. I suggest you have a notepad out and come up with questions that you can send me, and I can post the answers to those questions. We said that this is a min term, A naught, B naught. So think about how you would implement that. There's 4 outputs here. There's 2 inputs. So how would you wire this up? Well, it's just an AND gate. And you also need inverters for here. So A through an inverter, B through an inverter, both of those into an AND gate, and that gives you this. Likewise here, A goes to an inverter, B doesn't. Put them into an AND gate, and on down the line. So the first file that we're going to look at is the 2 to 4 active high decoder with no enable. Now I've got it highlighted. Hopefully you can see it. Let me make sure that's centered. I can blow this up a bit. There we go, 250%. So I realize if you're looking at this on a phone screen, it's going to be kind of small. Hopefully you can have a laptop or a desktop or a tablet to look at these videos. So here we go. No enable line, just a 0 and a 0 means this one is active. 0, 1 changes this one to active. So look at how this is wired. We said this is A naught B. There's A naught, there's B. If we change it to 1, 0, we get this output active. And 1, 1, we get the final output active. But no matter what the value, without the enable line, something's going to be on over here. All right, let's close that one down. And let's look at the active high enable decoder with an active high enable. So how could we get this functionality that we just talked about? Where 0 zeroes everything else out, but a 1 allows the normal operation. Well, you could think about it as D0 is equal to EN A naught B naught. So that's what it is. D1 is equal to EN and A naught B. So again, just taking the truth table, stuff we've learned in the first few weeks of class. So just add an extra input to each AND gate and have an enable line. If it's a 0, it'll zero it out. And if it's a 1, then it really has no effect and you get the same operation. So let's go back now and look at our 2 to 4 active high decoder with active high enable. That's what AH stands for in these file names. So here's our enable line. Notice that it's a 0. We just run it into each of these gates, and so it doesn't matter what else is going on. None of the outputs are going to turn on. But now as soon as we enable this device, now we get the same behavior that we saw before. We can also have an active low enable, and that just means that we have the opposite effect here. A 0 turns everything on, a 1 turns everything off. So how do we do the opposite? We just put a NOT gate right here. And so that's this third file, active high decoder with active low enable, AL. So here it is, 0, the decoder is enabled. If I turn it to 1, then it turns the whole thing off. And that's it for the active high decoders. We can also have an active low decoder. So these are called active high because a 1 indicates it's on. We can also have everything be 1 except for the one that is active, and so that's an active low decoder. The low, the 0, means it's the active line. So we'll look at that on paper. So this is an active low enable. Again, you have both kinds. You can have an active high enable, which means a 1 enables it, or an active low enable, which means a 0 enables it. D0, D1, D2, D3. And because it's active low, we have a bubble here as well. So let's look at the truth table for this. If enable is 1, we don't care. Everything will be on, but not active. Everything will be high. Now, if we enable it with a 0, because it's an active low enable, so this one becomes active. So the 0 is for active. With active low. You can also have an active high enable with this type of decoder. So again, we'll go back to Logisim, take a look at the circuit for this. And we'll do the active low decoder with an active low enable. So we've just replaced the AND gates with NAND gates. So a 0 here has enabled it. Notice I've labeled this EN not. A bar over the top would be a bit more proper. This is still correct, but in printed literature, if you looked at the data sheet for the 74138, it most likely has a bar over the top, but maybe not. So if I put this to a 1, everything is on, but not active, because this is an active low decoder. And it doesn't matter what I do over here. Now if I change this to a 0, I enable it, and because my input is 1, 1, this line will flip to 0. So that's the basics of how a decoder works. Please let me know if you have any questions. What do we use a decoder for in computer hardware? In the computer architecture class, I guarantee you're going to see these devices again. This class sets the foundation for Computer Engineering 4700. So what you can do is you can select or signal one of several different connected devices. So something like this. The CPU will set these depending on what it wants to signal. And here you might have the sound card needs to get a signal. Here you might have a CD, DVD, hard drive. A very simplified picture of this, but that's the idea. You'll learn more about that in computer architecture. Also, selecting memory. And so let me pull this diagram up. So, very simple diagram. Maybe it doesn't look simple. I'll write the address up where I got this in a moment if you want to take a look at this. This is about memory system designs, but I wanted to point out here's the decoder, 2-bit address. And if this line is active, then we are looking at this row in memory, an 8-bit value. If we use address 01, we'll select the next row of memory here. If we use address 10, we'll get this row of memory, these 8 bits, this 8-bit value, and then finally over here. So, again, you'll learn a lot more about that in computer architecture, but I just wanted to point it out, you know, why do we cover decoders, what use are they, and this is it. So now let's move on to what types of problems are you going to see with this. Here's a test and a quiz type problem. Well, we've talked how the decoder is min terms. Well, we can use this to implement functions. We've talked about 2 to 4 decoders. We could also have a 3 to 8, 4 to 16, 5 to 32. You can also use smaller decoders to build bigger ones, which we'll get to that in a moment. So, let's say we're given 2 functions, f of a, b, c is equal to the sum of the min terms 0, 2, 3, 7, and g is equal to the sum of the min terms 1, 4, 6, 7. Use a 3/8 decoder with active high enable. So we have 3 inputs, means we have 8 outputs. And there we go. It's also an enable line. Since we're implementing a function, we just tie this enable to 1. So here's our min term 0, 1, 2, 3, 4, 5, 6, 7. So for f, we need an OR gate. And we'll take 0, 2, 3, and 7. That's all there is to it. For G, we take 1, 4, 6, and 7. There you go. Just remember, inside here there are AND gates implementing min terms. So let's look at using an active low decoder. And we'll use active low enable. So an important part that you put in the enable line, if you're told that we have one, 0 to enable this one. A, B, C. 0, 1, 2, 3, 4, 5, 6, 7. And remember, inside of here are NAND gates. So we do NAND to NAND. So the top one was, again, 0237, 0, 2, 3, 7, and that's F. The other one is G, and we have 1, 4, 6, and 7. That's all there is to it. Fairly straightforward there. All right, so as promised, you can build a larger decoder from a smaller decoder. So implement a 4 to 16 decoder using 2 to 4 active high decoders with active high enable. So the concept or idea behind this is to use one decoder to enable one of 4 other decoders. So if we put A and B on one decoder, when it's 0, 0, it can enable a decoder that has these 4 values. So that's decoder, we'll call it 0. Next 4 rows, A and B has this value. And CD loops through the same values. So that's decoder 1, is what we'll call that. And I'm going by these values over here. So when A and B is like this, it'll enable this decoder. And this may be an example you want to look at a couple times. I promise you'll see it on quiz and or test. Call this decoder 2. Call this decoder 3. So here's A and B. 0, 1, 2, 3. When A and B are 0, 0, we go to another decoder that has C and D in it. We call this D0, D1, D2, D3. When A and B are 0, 1, they'll go to another decoder. So it's these four values here. 4, 5, 6, 7. Next, still have C and D over here. We have D8, D9, D10, D11, 8, 9, 10, 11, and then the last one. And these are all enable lines. D12, D13, D14, D15. And over here we have an enable line. Leave this as enable. So basically the idea is that you put this all in a big box now, and it looks like this. So what we have up here went inside of here. Let me show you something on Logisim. And like I said, I promise you're going to have to do this. And I might even make you do some stuff on Logisim, since you'll have extra time. So what I'm going to do is I'm going to make a new file here. And what I want to do is I want to take that 2 to 4 decoder that I showed you earlier and pull it in as a device on here. Logisim has a built-in decoder, but I want to use the one that I made. So you go to Load Library and Logisim Library. And I'm going to have to navigate to it. So I'm going to that 2 to 4 decoder with active high enable, the example we did on paper, and adding that as a library. And notice now here it pops up over here. I've named everything correctly. And now I have that decoder that I can use. If you mouse over it, it should tell you what the inputs are. There's A and B. These are not giving me values. And then here's the enable line. So I want to take this and build what we just looked at. So I'm using Control C, Control V. Actually, I can do better than that. Now that I've got 4 together, copy all of them, pull them down, and now I can do even better. Good example of exponential growth there. All right. If I was really slick, I would have copied all the wires too. I didn't quite line them up the same way. lined up the same way. That a little bit. All right. Label this as enable. Let's go with A. Call this one B. Let's see, good way to get C and D. I'm just going to put them up over here. I think that'll be the best way to make it the neatest as possible. There's C, and here is D. Label location on the north. Call this C, and call this D. I don't want to go any higher. Notice all our outputs are still off right now. And I know not everything's connected, but that's really because the enable is off. We're not enabled. So now let's look at if we enable. There we go. 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1. So notice these stay the same, kept that one enabled, all the others disabled. Alright, so I'll post this one as well. Let me save as. But now let's look at what happens. You know, what if we don't put A and B here? What if we put C and D out here? What happens? Well, this is a brief sketch. Here's C and D. Here's A and B. So what values go here? Well, C and D is going to be 0, 0 all the way down. AB goes through these four values. So what this means is that we have 0, 4, 8, and 12 on this decoder. I'm not drawing all the lines, but let's just look again. So over here, C and D are 0, 1. And so here we have 1, 5, 9, 13. The next one we would have 2, 6, 10, 14. And the next one we'd have 3, 7, 11, 15. So you can set the inputs however you want it changes the order of the outputs. And that's okay. All right, homework 4, there's a question where you're only allowed to use decoders and you don't have any inverters. And so you can build a decoder, you can build an inverter from a decoder. This isn't the only way to do this problem. But if we hook up this decoder like this, 2 to 4 decoder with a Z and a 0, write an expression for these lines. I'll give you a hint. Another will be equal to not Z. So then this becomes your inverter. You put a 0 here, a Z here, and a 1 here. And then if Z is a 0, one of these lines is going to be a 0. And if Z is a 1, one of these lines will be a 1. So let's take a look at another type of problem. And first we're going to have to look at a different type of decoder. This is the decoder you're using in Lab 5-3. It's actually covered in the book. Standard device. I brought a couple of these chips home because might be using them for Lab 6 as well. And I'm hoping I'll have a chance to build a circuit for you right here. We'll see if I have time to get that done. Alright, this lecture has gone on for a bit, but we're not too far away from the end now. We have this example, and then one more we'll talk about in the book. So that's not too bad. I'd like to keep the video shorter, but like I said, we're covering one topic. This is probably the last big topic in this chapter. So, I don't want to redraw this, so I'll just point you to the book and pull it up here and let you look at it. 74138 decoder. It's active low. That means a 0, it means active. It has 3 enables. Enable 1, enable 2, and enable 3. So this is active high, active low, and active low. The lettering is different. Be careful about this. It goes CBA. Most significant bit, least significant bit. EN1, EN2 not, EN3 not. And the outputs are labeled Y0, Y1, Y2, Y3, 4, 5, 6, 7. So see the truth table, table 5.3, and like I said, this is used in Lab 5-3, this device. So here is the truth table that we're looking at for this. So again, if enable 1 is 0, Doesn't matter what anything else is, it's off. If 2 is a 1, doesn't matter what anything else is, device is off. Likewise for 3. But if we have a 1, 0, 0 on the enable lines, then it operates as normal. Let me see if I can pull up the data sheet while we're talking about this. I've should have posted it in the labs. Maybe I forgot. So you don't have to worry about this since, again, we're not doing this lab physically speaking, but one of the outputs is on this side of the chip and all the other outputs are on the other side, so that's something that can be confusing. There's the circuit diagram for this decoder. I've already implemented this for you in Logisim. And notice for our truth table, they use H's and L's. So they've labeled theirs a bit differently than the book did. Use this. And their truth table is, well, first of all, let's look at the enables. Enabled 1 and 2 are the low ones. My Logisim circuit follows this. Enable 3 is the active high enable. Over here, notice that this is the most significant bit, this is the least significant bit. So they kind of did this backwards. So 0, 0, 0 across from the way they've written the table, this output is active. Next, 1, 0, 0 makes output 1. So this is the least significant bit. So you could almost read it 0, 0, 1 in binary. 0, 1, 0 for output 2 right here, and so forth. So just be aware of that. So, like I said, I want to look at example 5.1 in the book. So we want to use 4 decoders, 4 of these devices, and these are 3 to 8. We want to build a 5 to 32 decoder. And so you can read through this paragraph, look at it in the book, it gives some explanation, but we're only allowed to use 4 of these devices. So I'm going to go back on paper now and explain the thought process, and then we'll go through it all in the book. This is actually the first example they go over for decoders. I changed the ordering a bit from what's in the book. And so the idea here, instead of using a decoder to enable one of other decoders, we'll use A and B to enable one of 4 decoders. So again, I'm going back to the notation in the book, and in the book they're labeled like this. And so the idea is we want this kind of situation. A and B 0, 0 to enable this one. So this is 0 through 7. The next one, again, C, D, and E. We want A, B to be 0, 1. And so this will give us 8, through 15. For the next device, we have 16 through 23. AB will be 1, 0. And for the last device, we have 24 to 32. AB 1, 1. And sadly, I didn't leave myself enough space here, so we'll have to go on to the next piece of paper, but you can always pause and catch up and write this down, or just use the print off of the scanned copy of notes. So here's my 4 decoders. These are my A and B values that I showed you from the previous page. And here I'm going to choose my values for my enable lines on each decoder. So to enable this decoder, well, to enable all of them, I need a 1, 0, 0. I'm going to use A and B to achieve that. So if I just connect A up here and B up here and put a 1 on enable 1, that decoder will be enabled. So for this, when I want this decoder enabled when A is 0 and B is 1. So I can put B right here, put A right here, put a 0 right there. Swap it over here. Put B here, A here, and a 0 here. Any value of A and B other than 1, 0 is going to cause this decoder to be off. And then finally here, I am going to need a NOT gate. Put A here, I'll put B naught here, and put 0 right here. And you could swap these. You could swap this many different ways, but I believe this is the way they do it in the book. It's the way I've got it in my notes. And so now we'll look at there it is, the final rundown. All right, so as promised, one more problem here. So here we have a 2 to 4 decoder that we're given, and we're told to implement these 3 functions. And so there's a couple steps here. We could take this decoder and build a 4 to 16 decoder, because we have 16 different possible minterms up here. 16, 16, 16. So we need a 4 to 16 decoder, and then simply use NAND gates and take all the individual minterms, which you can see I've numbered in my book. We need a 9 input NAND gate here, a 10 input NAND gate here, and an 8 input NAND gate here. So that's one way to do that. However, we can reduce those number of inputs if we swap, like I was talking about before. And that's where we take C and D and put them on the outside and use A and B on these gates, these decoders. And we actually can take this one step further, and I will show you that in a moment. That's on the next page. So the key is here, F has 3, 7, 11, and 15. So 3, 7, 11, and 15. So we don't have to run all of these inputs into a gate. We just take this line. And so we've gone from 4 inputs down to 1. And then we'll have to get the rest of the things for F, and that's 0, 2, 4, 8, 10. We have a similar pattern for G, 1, 5, 9, 13. 1, 5, 9, 13. So again, we connect right here to G into G's NAND gate instead of this, instead of all of these individually. And similar pattern for H. We have 2, 6, 10, 14, which is all of these. So just take this enable line. We can do even better. I will say there's a typo in the book. X this out, break this wire here, and then connect it here. And what this ends up getting us is a 4 input gate, a 5 input gate, and a 4 input gate. No, I'm sorry. That's another 4 input gate. They're all 4 input gates. And the way we get to this is because we notice this group of 4 in each place. CD, C0 D, CD 0. So remember, these outputs are really just min terms. So we use this here. And then the other saving feature is the corners here is B0 D0. So we use another decoder to implement that. And then this group of 4 through the tunnel is B D0. And so then we're just left to pick up a 15 and an 8 here, a 15 and a 12 here, and a 4 here. And we can get that with just 2 additional decoders. So, you know, I believe I mentioned the State of the Union, the last video, that there's no way I can really make this a closed book test moving forward. You know, you may see something similar to this on the test, but you'll have time to do it. As of right now, I'm not planning on giving you like just a 2-hour time limit because I know everybody's internet can be sporadic. I'm planning to give you like a 48-hour window to complete the test, and so I understand that I'll allow you to use your book, but I'll make the problems harder than they would be if you had to do it in class without any materials. It's still to be your own work, but you know, you may see something similar to this on the test. And like I said, you'll have time to work with it and ask me questions and work through it. But not something you need to memorize by any means. Do take a look at this. All right, that concludes decoders. And next we'll talk about encoders. It's a page and a half, very brief, and then we'll talk about multiplexers and demultiplexers, which is again just a couple pages. We're not going to talk a whole lot about those, but that'll be the next video. So this is the last long video that we have on this chapter. Everyone stay safe out there. Please stay in contact. Let me know if you have any questions, and I'll be posting a new video soon. Thank you.